Math doesn't necessarily need to be your strong suit in order to get better at data structures and algorithms. Instead, you need to get good at drawing boxes and arrows. What is a data structure? It's a specific way of organizing data based on what we know about how we'll be using it. Now, how does a computer see a data structure? It just sees a bunch of data in memory. What it needs is to be told which data is important and what it needs to process. How does it do that? Well, we tell it. This is done through using pointers, or a pattern of some kind. Now, what is an algorithm? It's a sequence of tasks that need to be completed to get some result. Fundamentally, an algorithm is a transformation from one form to another. In the context of data structures, an algorithm is usually concerned with managing the data and not processing it. What do arrows and boxes have to do with this? Well, as it turns out, pretty much everything useful we do with computer memory can be abstracted as a bunch of boxes which represent data objects, and arrows which represent pointers to the data. Then there is the golden rule of data structures. The computer can only get to something if it has a pointer to that thing. Very often it finds new pointers in the object it found after following another pointer. Now, if you can wrap your head around these two basic parts of a data structure, we can combine them in beautifully complex ways to structure beautifully complex data. For a very simple example, I drew a linked list, which is probably the second most simple data structure. Now look at how many arrows and boxes there are. 5 and 7. From those two simple building blocks, we produce something more complex, but also more useful. So now, how do we add something to the beginning of the list? We need to break this into a few simple tasks that involves drawing more arrows. Create a new node. 2. Make the new node's pointer point to the first node. 3. Make foo point to the new node. We have just described an algorithm for how to add something to the beginning of a linked data structure. That didn't really take much math at all. Now we can think about how many steps it took to do this. It's easy, just 3. Will it always take 3 steps? Yes. But what if we wanted to put a new node at the end of the list? Then we would first need to get there. Then it takes as many steps to get to it plus the steps to put the new node there. Here's an algorithm. Start at foo and go to the end of the list. Create a new node. Make the new node's pointer point to the end marker. Make the last node in the list point to the new node. We can pretty much continue like this. Now what we need to watch out for is how long it takes to complete the task. This becomes a puzzle. Maybe we don't want to always have to walk to the end of the list.